that Bala Ayar. At present, he is a visiting professor in ICTS, one of our TIFR center at Bangalore. And earlier, his career is spent in most of the times in the Raman Research Institute, that's also at Bangalore. And at present, he is the chair of the Indigo Consortium. Since the inception of this, Indigo is this Indian LIGO. And also he is a representation of the Gravitational Wave International Committee since 2011. And as I said that he was in RRI, he was the chairman there at the end of his career, the theoretical physics group for 2 terms, and retired as a senior professor from that institute. And his principal research interest in the last 2 decades or more related to the computation of high accuracy gravitational wavefront. I have to read it because there is some important things are there. I should not wrongly spelling or not interpret properly. So the wavefront, this is a spiraling compact biranes of neutron star and black hole using multipolar post-Minkowskian methods. And this is the method, this high accuracy wavefront underlie the constructions. This is the method, it was mainly used to the gravitational wave template used in the gravitational wave data analysis pipeline in the detector LIGO and Vigro. So that's now you can understand he is an expert in this altogether this astrophysics, but the gravitational wave, that is his main bread and butter, and he knows the in-depth of this, how to analyze the gravitational wave and how to develop the softwares. So for that, today we choose him to give a lectures on the gravitational wave, a new window to the universe. Bala.
Okay, let me begin by thanking Govinda and the organizers of the school for the opportunity to address all of you. And as you will see, I will try to bring to you the fascinating story of the first detection of gravitational waves and try to show how there is a common interface between what you do in high energy physics and what you have been doing in gravitational wave research. So at the end of the talk, I hope I convince you that this is a new window which has opened, and therefore you cannot be blind to what happens in this particular area. So I begin my talk with a basic primer of gravitational waves, trying to put together what you really need to understand what happens in this particular area. General relativity, as you know, is Einstein's relativistic theory of gravity, and even after 100 years, it is agreed that it's an epitome of mathematical elegance and conceptual depth, but importantly, observational success. In Einstein's view, gravitation is synonymous with space-time geometry and mathematically described by the curvature or distortion of space-time. Einstein's equations are a system of 10 nonlinear partial differential equations, and if you read them from right to left, it tells you that matter tells space-time how to curve, but surprisingly, space-time also tells matter how to move. What are gravitational waves? Gravitational waves are freely propagating oscillations of the gravitational field. Physically, gravity manifests as a tidal effect. So one can say that gravitational waves are oscillating tidal gravitational fields which propagate out from the source. So there is a natural question which you would like to ask. Do Einstein's equations have gravity wave solutions just as Maxwell's equations admit electromagnetic wave solutions? And this was answered by Einstein himself in 1916 using a simple version of general theory of relativity, which we call linearized gravity. A couple of years later, he gave what is called as the quadrupole formula, which is nothing else but the analog of the dipole formula for radiation, which we have in electromagnetism. This basically tells us that the gravitational wave field falls off as 1 by r, and it is given by the second time derivative of the quadrupole moment. If you take this formula and put it for a system of mass m moving with a velocity v at a distance r, it takes a very simple form, which if you apply to a dumbbell made up of 2 trucks separated by a couple of meters, rotating at about 1 kilohertz, gives you a value of about 10⁻⁻39. And being very competent patent clerk, Einstein realized it must have a practically vanishing value in all conceivable situations. Such ripples would be vanishingly small and nearly impossible to detect. And as usual, he was right. It took 40 to 50 years for a conceptual framework to determine without ambiguity if gravitational waves exist in GR and what properties do these gravitational waves have. The basic question you are trying to answer is, do gravitational waves transfer energy or are merely an illusion because you are choosing wavy coordinates? The answer really came in this meeting in Chapel Hill, where Felix Pirani was one of the postdocs, and he pointed out in one of these papers there that the tidal effect of gravitational wave is unambiguous, irrespective of whether you have problems in trying to solve the generation problem, and they are given by the geodesic deviation equation. So there's no ambiguity in what gravitational wave should be. And in the discussions which happened at that meeting, which go under the name of the sticky bead thought experiment with Bondi, who was his mentor, one can say that the physicality of gravitational wave was resolved in this particular meeting. In this meeting was Joe Weber, and therefore he decided that it was important to experimentally look for gravitational waves, and he decided to build a bar detector. So one can say that the quest for gravitational wave detection was born in this particular meeting. See, in parallel, theoretical work looking at gravitational waves in the full nonlinear theory happened at King's College and in the work of Chandrasekhar, which I will talk about in the next slide. In the 1960s, Chandrasekhar addressed the radiation reaction problem. He asked the question, how does the emission of gravitational wave affect a system if it is self-gravitating? Chandra was the first to show conceptually that the radiation reaction problem could be solved for continuous physical systems, and following Trotman, he assembled the essential ingredients required to solve this particular problem. Go beyond linearized gravity by using the nonlinearities of the gravitational field, use retarded potentials to describe the solutions, and try to expand them in the near zone so that you can implement the outgoing boundary conditions. So all these technical complications allowed him to iterate the Einstein's equations and show that the energy and angular momentum radiated as gravitational waves was correctly balanced by the loss of mechanical energy and angular momentum by the system. So this work essentially gave the astrophysicists confidence that GR was physically reasonable and well behaved. Of course, the mathematical relativists had some problem with this particular treatment, but that, as I will explain, also was sort of solved a little later. So we are in a situation where in the 1960s, Joe Weber decided to build a resonant bar detector, a detector which rotates, which sort of oscillates at a particular frequency, and the kind of sources he was looking for were supernovae. These detectors are narrowband detectors, and in a sense, he founded the particular field, but one may consider him to be a tragic pioneer because in 1969, he made a claim for the gravity wave detection, but other groups could not verify it. So in a sense, he made a wrong judgment when he basically thought that he detected gravitational waves. And it was in another 50 years when the advanced LIGO really detected the gravitational waves. So this paradigm shift required two things to happen. From bar detectors, one moved to laser interferometer detectors. Unlike these detectors, which are narrowband, the laser interferometer detectors are broadband. And this is important because from supernova as prototype sources, we now believe that the prototype sources are coalescing compact binaries. And this was also sort of came to a conclusion in this conference, which happened in 1978. So let me just recapitulate and tell you how paradigm shifts really happen. So essentially, from a fundamental discovery of a particle like a neutron, you go to an astrophysical object called a neutron star, and from that you come to objects called pulsars, which can act as very accurate clocks by which you can do some things which I will sort of describe in the next slide. So 1932, Chadwick describes the neutron. Almost in that same year, Landau talks about the existence of neutron stars, just as you had white dwarfs predicted by Chandrasekhar. And the astrophysicists Bade and Zwicky in 1933 said that neutron stars could be the end states of supernova explosions. And theoretical work by Oppenheimer and Volkoff essentially showed that these stars should have a mass limit, which we today know is a few times the mass of the suns, but the radius is very, very small. It's like the radius of a city or something like that. So you have a star as massive as the sun. So essentially, it's a star at nuclear density. So a neutron star is a giant nucleus, but nobody knew how to look for a neutron star. Then again, a graduate student, Jocelyn Bell, made the serendipitous discovery of an object which we call pulsars. And then it turned out that when you looked at these particular objects which are rotating very fast, they had to be nothing but rotating neutron stars. Again, another graduate student comes into play, Hulse, who was working with Joe Taylor, and they were making a survey of pulse to look for more pulsars, and they discovered an unusual pulsar in a binary system. So in a sense, instead of having a dumbbell on the earth, you have a dumbbell made up of two neutron stars in the heavens. And if you really look at this particular system, and then you ask the question, if general relativity is right, this system should emit gravitational waves, and therefore instead of moving on a fixed orbit, it should inspiral inwards. There are techniques by using radio pulsar techniques by which you can reconstruct this particular object, and it basically showed that whatever you predict from Einstein's equation is exactly what you see in this particular system. For the discovery of this particular object, which is a new type of pulsar, Hulse and Taylor received the Nobel Prize, and the study basically said it opened up new possibilities for the study of gravitation. For our story, it's a watershed event because it demonstrated that gravitational waves are physical, they are accurately described by Einstein's general theory of relativity, and if you take systems like this in their final stages, when they are about to coalesce, they would be the prototypical sources for detectors using laser interferometer gravitational wave detectors. So this essentially comes to ask the question, what happens if you want to detect gravitational waves? You should know what its effect is on a physical system. So if you analyze the equations of gravitational waves in general theory of relativity, one can show very easily that the tidal force is oriented either like a plus or a cross. So if this kind of force field falls on a system of particles, then it will be squeezed in a time-dependent, oscillatory time-dependent manner. So if you want to detect gravitational waves, you should measure the amount of squeeze which happens in such a system. So to quantify this quantity, you describe a quantity called gravity wave strain. If you have a system of length L squeezed by an amount delta L, you take the ratio of delta L by L, and this is called the gravity wave strain. So if the strain is sort of fixed, if you want to have a larger value of displacement or squeeze, you need a larger system. And that is exactly what you set out to do. And therefore, you do a very simple calculation. You take this binary pulsar-like system, which is made up of two neutron stars, take it in its final stages when it moves at very velocity, is close to the velocity of light, put it in the nearest cluster of galaxies, which is the Virgo cluster of galaxies, and you find that the strain is of the order of 10 raised to minus 21. So from 10 raised to minus 39, you have gained almost 18 orders of magnitude by going to this particular system. But then, even if you can build an interferometer which is of the order, which is of a kilometer scale, the displacement will be of the order of 10 raised to minus 18 meters. It is a nuclear fraction of a nuclear dimension, 1,000th of a Fermi. So if you really want to detect gravitational wave, then you really need the accuracy to measure such a small displacement. And that essentially is what you basically do. You basically use the interferometer as a transducer to convert the gravitational wave to a photocurrent, which is proportional to the strain amplitude. So this is the basic principle of a laser interferometer gravitational wave detector. And if you really want to ask what is the displacement, what is the challenge experimentally involved, just compare it with what happened during the Michelson-Morley experiment. If you analyze that, essentially you are making a displacement measurement of the order of a nanometer. And what you really need to do here is 10 orders of magnitude larger than that. And obviously, if you assume that there is a 10 order of magnitude every 10 years, it takes about 100 years to make the detection, and that's exactly what
We'll do from there. Yeah, just okay. You can start.
Shall I continue?
Yeah.
So that was one particular challenge. The other thing is, as you know, if you really look at the an instrument on the Earth, there is seismic motion, and the seismic motion is of the order of a nanometer at the frequency range in which we are going to be interested in. So if you really want to measure something smaller, you really have to reduce the seismic motion by again a factor of 10 raised to 10. So there are two factors of 10 raised to 10 which you have to sort of challenge, and only then this experiment can succeed. And obviously the fact that the experiment succeeded basically means that these two factors of 10 were conquered. I think this should be put again. Yeah. Now, when you look experimentally at what is the smallest displacement you can measure at a particular frequency, it depends on the noise at that particular frequency. So, for example, at these frequencies, you are dominated by the photon shot noise, at these frequencies by thermal noise, and at the lower frequencies by the seismic noise. So you really need to, to get these sensitivities, you really need to use different aspects of physics. For example, you use high power laser to get this sensitivity. To get to this particular sensitivity, you really have to build low thermal noise mirrors. And as I told you, if you really want to conquer the seismic noise, you really have to have the best shock absorbers in the world. And therefore, by a passive isolation system, which gives you a factor of 10 raised to 7, and an active isolation system, which gives you a factor of 10 raised to 3, that factor of 10 raised to 10 is sort of achieved. The interferometer is also has to be kept in a ultra high vacuum. So you need a very large, very high vacuum system. And it's a complex system. So really to keep it optimally running, you have about 300 control loops. So essentially, I think this talk is merit in this particular meeting because this experiment really involves instrument science at the frontiers of physics fundamental limits. The LIGO project essentially consists of two sites, but at one particular site in the same beam tube, two detectors were put. So LIGO can be described as two sites and three detectors. The detectors are put as far away in the US as they could. The light travel time between these two is about 10 milliseconds. And at each of these particular sites, you have a very large number of systems to monitor all kinds of noises to which the system is really subject. And the strategy is that if you are seeing an astronomical kind of source, you should be able to see it in both these particular sites. So the coincident detection between the two LIGO observatories is really used to reject transient environmental disturbances. We have a colleague interferometer in Europe, which is called the Virgo detector, which is near at a place called Casina. It's a smaller detector, about 3 kilometers long. And as I will explain to you, it's important to have a global network if you really want to do astronomy. This is basically because of the fact that if you look at the antenna pattern of a single detector, it has a broad directional response. The gravitational wave detector is not like our eyes, but it's like our ears. And therefore, if you want to do astronomy and localized sources, you need a global network of gravitational wave detectors. And if you have a global network, you can do triangulation by using the different time delay arrival at different sites and reconstruct where the source is in this particular sky. So a global network is really required if you want to do astronomy, and that is the reason having the Virgo detector was very important. Now, after talking about the detector, let me come to the source which we are talking about. The source which we are talking about is a binary system, and a binary system which is going around each other. Now, just simple Newtonian physics tells us that if you have a binary system going around each other losing radiation, it will start coming inwards. Therefore, the frequency will increase. Because it is coming inwards, the gravitational field is becoming more. Therefore, the amplitude of the wave will increase. So you have what is called as a chirp waveform. as the system in spirals. If you analyze the equations in general theory of relativity, it turns out that at some particular point, there should be a plunge which happens because there is an unstable orbit there. So therefore, the system sort of merges, and after it merges, it becomes one binary, one kind of system. And that system, if it is a black hole, can ring like a bell, and that is what is called as the ring down of this particular system. So the important point you have to keep in mind is that in the frequency band of the detectors, you have these binary systems, and depending on their mass, they will coalesce either in the mid band, or if you have a neutron star binary, it sort of coalesces towards the end. This is the qualitative picture which you have, and the analysis of the general relativistic equation bears it out more accurately than what is given there. So now I have told you something about the sources. Now let's ask the question, how do I do the data analysis? Even though you are talking about gravitational waves from neutron stars and black holes, if you compare to the noise of the detector, you are in a situation where you have a weak signal which is buried in the noise of this particular detector. So if you really want to say something about the signal, you have to use an engineering technique which is called match filtering, both to detect this particular signal and to do parameter estimation of this particular signal. What is match filtering? I just explained it to you by using this. So what you basically do is you basically correlate this particular signal with the noisy data, and somehow if I don't see that, I don't know what I can do. Yeah, you can see that now. So you can see that when you do this kind of match filtering, at this particular point, there's no correlation. But when you match this exactly, you suddenly will pick up this particular correlation. So this is match filtering. So if you know what you are looking for, you can find it. That is really the catchword for match filtering. But you don't know the parameters of this particular source. So you don't know what this waveform will really look like. So you really have to construct not just one waveform, but you have to use a bank of templates. So you have to construct a template waveform. If the matching to the phase is not very accurate, the correlation will not be as strong. So if you want to succeed in match filtering, you need an accurate model of the signal, and that you can calculate by using the best theory of gravity which you have, which is the general theory of relativity. And therefore, the theoretical challenges emerges. If you take a self-gravitating body, for that, the velocity square is proportional to the potential Gm by R by the Virial theorem. So if you want to calculate higher order corrections in V square by C square, you also have to deal with higher orders in G. So you cannot work with linearized gravity. You really have to look at the nonlinear aspects of the general theory of relativity. And therefore, at the end of the day, or at the end of a couple of decades, you can find a formula which tells you what is the gravitational wave phase when the two binary systems are about to sort of coalesce. And this essentially is the work which I was involved in with my colleagues in France. And this, was the work on source modeling. Once somebody produces for you a waveform, you have to do the gravity wave data analysis. And this work was sort of pursued by my distinguished colleague in IUCA, Sanjeev Dhurandhar. So almost when the LIGO project began in the US in the early 1990s, the two groups which we had here essentially was involved in the two very critical aspects of this data analysis. Starting from the waveform at the in-spiral phase, nowadays, today, of course, you can improve upon this by using resummation techniques, using numerical relativity, and using other numerical methods. But this is the starting point for doing any data analysis in general theory for gravitational waves. Now, if you really ask the question, how many parameters does this waveform depend on? It depends on 15 parameters. It depends on the intrinsic mass, the intrinsic angular momenta of the two bodies, and on the extrinsic parameters, which tells you where it is located, how far it is, and the two parameters related to the coalescence phase and the coalescence time. So because it's a 15 parameter thing, starting from the data, which involves calibrating the instrument very accurately, characterizing all sources of noise, You start from the raw data, extract out the gravity wave signal, and then, as you do in high energy physics, you use Bayesian methods to extract out the parameters of this particular source. And that is exactly what is shown here, where there is a waveform which is experimentally observed in blue, and then theoretically you try to fix it with what is the best theoretical prediction for it by changing the mass and by changing the distance, and try to make the best fit which you have for it. So when you do that, you can extract out all the parameters of this particular source. So not only can you detect this particular signal, you can also determine what the parameters of this particular source will really be. So this is a game essentially which you really have to play. Having the templates is very crucial to get an exact estimate of what the parameters of this particular source is. Now, qualitatively, you can really see that this really tells us a lot about what the source really is. Suppose you have a binary black hole. A black hole is almost like a point object. So if you try to ask what kind of waveform you can have, as I told you, it will have an in-spiral, a merger, and a ring down. And in the in-spiral, that waveform can be affected by different effects. If the object is spinning, there will be some precession effects. Because of nonlinearity, there are what are called as tail effects. Because the black holes have horizon, there are black hole absorption effects. And as I told you, finally, when the system coalesces, it rings like a bell, and there are quasi-normal modes. Essentially, this is the waveform which you have, characteristic of a black hole. But suppose you have a neutron star, what would happen? When the system is very far away, it will not show any deviation from the black hole waveform. But as you come closer, because of the tidal effects, the waveform will start deviating from the point particle approximation, and the amount of tidal distortion will depend on the equation of state of matter which the neutron star is made up of. So the tidal information which you can extract from astrophysics tells you something about the equation of state of matter, neutron star matter, at very high densities. So this is where you make a connection from an astrophysical observation to something which you are interested in the laboratory. Next, you ask the question, what are the properties of gravitational waves in general theory of relativity? Then you notice that from the equations you can prove that as in electromagnetism, gravitational waves travel with the speed of light. They are transverse and they have two states of polarization. There's no monopole or dipole radiation, basically because gravitation is described by a spin-to field, and therefore there are conservation laws related to energy, linear and angular momentum. This prevents you from having monopole or dipole radiation, and the dominant radiation is quadrupolar. But there are differences, because gravitational interaction is 10⁻39 times weaker than the electromagnetic radiation. So you can say that gravitational waves will propagate unperturbed as they interact very weakly with matter. Therefore, you can have gravitational waves if you have a supernova event. From the heart of a supernova, you will be able to see gravitational waves if they are emitted. Similarly, you can go closer to the Big Bang than you can by using the electromagnetic radiation or the cosmic microwave background radiation. So these are the differences which you have, which are going to give you the advantages. Now, the properties of gravitational waves which I mentioned are characteristic of what happened in the general theory of relativity. But if the theory of gravity is a different theory of gravity, there can be differences from the prediction which you have, and therefore eventually it will allow us to test the correctness of the general theory of relativity. For example, do gravitational waves travel at the speed of light? Does it have only two states of polarization? These are the kind of questions which you can try to answer. So that finishes my primer on what you really need to understand the gravity wave observations. So now I come to the first direct detection of gravitational waves, which is called this particular event, which happened on 14th September 2015. The LIGO detector, advanced LIGO, the first observational run was supposed to start on September 12, and just a couple of days later, something remarkable happened. The results really come from the LIGO scientific collaboration, and it is sort of supported by the NSF, and therefore this is the acknowledgement to that particular funding. So what happened just as soon as the detector was switched on was that these two LIGO observatories, they detected a coincident gravitational wave signal. So I had sort of told you that if it's an astrophysical signal, you should be able to see it in both the detectors, and that is exactly what happened. You saw two signals, and they came within 7 milliseconds. It was a very strong signal, so technically we say that it has combined signal to noise ratio of 24. And as I told you, by what I explained to you in the primer, once we have a signal, we can reconstruct its parameters. So we can say that it's two black holes coalescing, and then what the final spin is, how far it is, and if you use cosmology, what is the redshift of this particular source. And you can see here, it's a very violent event because in about 0.2 seconds, 3 solar mass is converted to gravitational waves. So it's a very, very violent kind of event. And as I sort of explained to you, the strength of the signal depends on this combination of binary masses, which is called the chirp mass. This is the mass dependence. So what we really do is we look at the observed data. If you slide the data by 7 milliseconds, they essentially coincide with each other. Because we know the parameters, we can integrate Einstein's equations numerically and calculate what the expected signals should be. And if you subtract one from the other, what should be left should be consistent with the noise. So this kind of exercise is what tells us that what we are claiming is what we are confident about. The first discovery was not just about the first direct detection of gravitational waves. It had astrophysical implications because it was the first detection of a binary black hole that merges within the age of the universe. It was the first observation of stellar mass black hole whose mass was as large as 25 solar masses. If you want to create a solar mass, such a large solar mass black hole, you can say something about the environment in which this black hole can be made. The environment cannot have very large winds because then the mass cannot be very large. So the wind should be weak. And once you say something about the wind, it tells you something about the metallic content of that particular environment. It says that the black hole formed in a low metallicity environment. And as I sort of told you, that you can use the data to test general theory of relativity in a regime where the gravity is very strong and also time dependent. All this could be done. So it was not just about the detection of gravitational waves. A lot of astrophysical implications really came from the first discovery. It's really amazing that the gravitational waves really came from a binary black hole system at a cosmological distance. It was emitted 1.3 billion years ago, when on Earth, transition was happening from single cell to multicellular forms of life. So this is really amazing. You're saying something very precise about the universe on Earth when it was not even clear that we would be emerging. So that is really the strength of this particular observation. And this discovery paper had 37 authors from Indian institutions and citations to seminal papers, including Indian researchers. For us, it was a very important event because just 1 week after that, the in-principle approval of LIGO India project really happened. What is the LIGO India project? In 2009, the Indigo Consortium was formed, and the aim of the consortium was to extend the Indian footprint, as I told you, which was already there in source modeling and data analysis, to a pan-Indian gravity wave experiment. And therefore, in 2011, when an opportunity came, we made the possibility of a proposal for a LIGO India project. LIGO India is, if it gets its approval today, will be sort of taking its first set of readings into about 2030. There are 4 Indian institutions which are responsible for the execution of this particular project: RRCAT, IPR, IUCA, and DCSCM. The interest in the LIGO India project globally is for the following reason. As I told you, if you had only the LIGO Virgo network, the localization of sources in the sky is very poor in these particular directions. As I told you, the LIGO project consisted of 3 detectors and 2 sites. So if you take one of the detectors from Hanford and move it to India and create a LIGO India project, the sky localization is good all over the sky. And that essentially is the scientific reason why the LIGO people wanted to have the detector in India rather than in Hanford. So one can quantitatively estimate that on an average, the angular resolution improves by a factor of 4, and in some directions by a factor of 10 or 20. Again, what is relevant to this particular workshop is the fact that though the interest in LIGO India emerges from its interest in fundamental physics and in astronomy, what really challenges us or excites us is the kind of interface it has with technology and with experiments. So as you can see here, it involves precision experiments and fundamental tests, quantum metrology, laser physics, vacuum technology, optical engineering, sensor technologies, control systems, and so on. So there is a lot of implications if LIGO India would really sort of happen. The important point is that the discovery was so monumentous that just a year after the announcement was made, the Nobel Prize was given to Barry Barish, Kip Thorne, and Rainer Weiss. Being the experimenter on this particular project, half the Nobel Prize was given to Ray Weiss, and the other half was shared between Barry Barish and Kip Thorne. And the citation basically said, for decisive contributions to the LIGO detector and the observation of gravitational waves. Again, there is a kind of interface with the high energy physics community, because Barry Barish was a high energy physics kind of person, and he basically realized that if LIGO has to sort of succeed, it has to transform from a lab experiment into a large consortium activity. And therefore, he brought into the LIGO, he created what is called as the LIGO scientific collaboration, and that really had an important role in the success of the advanced LIGO. So in a sense, one can say that the detection of gravitational waves is celebrated as one of the greatest scientific achievements of all time, and therefore these 2 observatories have been designated as historic physics sites in the US. We are very fortunate because we lived in an area, in an epoch when on February 11, 2016, it was a repeat of what happened on November 7, 1919, when newspapers all around the world talked about a scientific fact. So if you look at the headlines on the newspapers all around the world on this particular day, it is about LIGO results. Of course, our Amul also had its own share of cartoons. So in a sense, it is really amazing that 100 years after that, the success of general theory of relativity and the discovery of gravitational waves. So Einstein, if wherever he is, would be very, very happy. That was about the first observational run. Now let's see what happened in the second observation run. During the second observational run, almost towards the end, the Virgo detector joined the observations. And just a couple of weeks later, the LIGO and Virgo discovered its binary black hole system. And the sky localization, as expected, was, instead of being hundreds of degrees, it was only 60 square degrees. So suddenly you sort of realize that the power of the global network is really achievable. And this really played an important role for what happened 3 days later. Though the Nobel Prize was announced on October 3rd, the community was really waiting to make an even bigger announcement on October 16th. And this essentially launched what we call the multi-messenger astronomy. What was seen on 17th August 2017 was the emission of gravitational waves from a binary neutron star. So you can see here that there is a very distinctive signal which lasts for about 100 seconds. And you can only see it by using match filtering. You cannot see it without doing the match filtering. And the signal to noise ratio is very large. It's almost about 32. And because we can reconstruct its parameters, we know that what we are seeing is gravitational waves from a neutron star. But that is not what was exciting. We know that we are seeing gravitational waves, but something remarkable happened with the gamma ray detector, which is the Fermi. So what we are seeing here is the gravitational wave signal, but almost very close to that, the Fermi also saw a signal. So now you ask this particular question. Of course, the signal is from the whole universe, so it could just be an accidental coincidence. Is it coming from the same source or not? So this is basically the question which you wanted to ask. And then you basically realize that because of the fact that you had three detectors, the sky localizations of the two sources, the black hole source and the neutron star source, is very small. So we warned our astronomy colleagues, please point your telescopes to these regions in the sky and see whether there is an emission from this region in the sky. And 10 hours later, the SWOPE telescope in Chile spotted some electromagnetic radiation from there. And 5 other observatories within the next hour confirmed that they were also seeing something from there. So this really was an amazing event, because this event or this region of the sky was observed by 70 observatories and more than 100 instruments. And this included the AstroSat from India, looking at the X-ray, the GMRT doing radio observation, and the Himalayan Chandra telescope doing optical observations. All these instruments tried to see whether they could detect some electromagnetic radiation from this region in the sky. So you basically see that not only there is a gravity wave radiation, on a small time scale, there are electromagnetic radiation, and after 9 days, one saw X-ray emission, and after 16 days, radio emission from this region in the sky. So you can see that this is a multi-messenger observation of a binary neutron star merger, and this paper in ABJ letters had 950 institutes, 48 follow-up groups, 70 observatories, and more than 100 instruments. So the important point is, as our colleague Metzger said, this was the most ambitious and emotionally charged campaign in history for any source, which lasted for about 100 seconds. So I like to describe it as the following. If the first detection was like the transition from silent movies to talkies, the neutron star event was like the advent of the IMAX, because you saw it in all possible wavebands. You can make sure that for this event, you can find out all the particular parameters. In particular, I want to point out to you, you can put an estimate on what is the tidal deformability this waveform is consistent with. And depending on what you assume for the spin prior, you can come up with some particular value. Therefore, what we promised you, we are delivering. From the measurement of this tidal deformation, we try to look at equations of state which will be consistent with that tidal deformability. And therefore, some equations of state could be ruled out by these particular observations. As the measurement of the tidal deformability becomes even more accurate, more and more information about the equation of state of neutron star matter will become available. So again, it's not just about the detection of gravitational waves from a neutron star binary. Of course, that is the first observation. But again, it is the first observation of gravitational waves and electromagnetic waves from the same source. Therefore, it supports the hypothesis that this gravity wave event was produced by the merger of two neutron stars in this particular galaxy. It was followed by a short gamma ray burst, and that gamma ray burst was followed by what is called as in astronomy as a kilonova, which is sort of powered by the radioactive decay of our process nuclei. So again, you can see here, this is where we connect with nuclear physics, high energy physics, and so on. And it is really surprising that we use silver and gold and platinum, but even till today, nobody knows where they are really made in the universe. So because of the fact that when you have these two neutron stars merging, there's a large number of neutron stars, our processes can really sort of happen. And therefore, in a process like this, you can make 50 Earth mass of silver, 100 Earth mass of gold, and 500 Earth mass of platinum. Don't go prospecting for it, but this is exactly what is sort of possible in this particular kind of process. This is a remarkable object because if you look at the ADS, on this particular object, almost 1,700 papers have been sort of written since the discovery. Even last week, the reanalysis of some earlier data basically shows that the kilonova was very spherically symmetric. This tells us something about what could be there inside this particular object. So you can see here that this is a remarkable kind of object, and it has done something which we really could not have imagined. The importance also is that in the future, just as we have had now gravity wave and electromagnetic thing, we also look for coincidences with neutrino experiments. So maybe in the future, there may be a source where you have a joint neutrino gravity wave electromagnetic observation, and that's something for the future. Using the gravity wave and the electromagnetic things, we can measure, make an estimate of the Hubble constant, and therefore you can do cosmology. And as I told you, there are many things you can do to test general theory of relativity, and this is exactly what was done in this remarkable kind of paper, where many predictions of gravitational waves in general theory of relativity was, limits were sort of put on them. So let me just sort of recapitulate what the revolution is. Just before the gravity wave window was opened, we knew about neutron stars and black holes by electromagnetic observation. And this is exactly what our picture was. This is the mass, and this is the electromagnetic observations, and these are the black holes. The moment you have opened the gravity wave window, we had this binary neutron star, again, this given here, and these black holes, which are a different population. They are higher mass objects, kind of. So in a sense, we have done something which is remarkable. When LIGO was proposed, it is an acronym for Laser Interferometer Gravitational Wave Observatory. People smirked because they basically said you have not even detected gravitational waves and you are calling yourself an observatory. What we have definitely demonstrated is that this O has been earned twice over, both in the discovery of the binary black hole and the binary neutron star, because we have revealed a new class of objects which were not seen by electromagnetic observations. So in the first observation run, we had 3 binary black holes. In the second observational run, we saw 7 binary black holes and 1 binary neutron star. And you will agree, this has been transformative. And therefore, it is interesting that when we made our data public, the Princeton group essentially could find 8 more binary black holes in this particular data. You may ask, why did we not find it? Essentially, depending on where you make your cut in your thresholds and so on, there can be sort of differences, and that is exactly what one is seeing here. So that is the first 2. So where are we today? Let me come to the current status. The third observational run has been basically completed. It began on 1st April 2019, and it had to be ended earlier because of the pandemic, because the laboratories had to be sort of closed. At the end of 2019, the Japanese detector was supposed to join, but because they couldn't sort of join during this couple of weeks, the Geo detector and the Kagra detector made some joint observations, and all the data from the O3 has been released publicly on this particular date. So from the first and second observational run, we had about 11 discoveries, but in the third observational run, because the instrument is more sensitive, we are seeing further, and therefore you are seeing much more kind of sources. So where are we today? The electromagnetic observations give you this and this. Today we have 90 coalescing binary objects. These are all transient, as I sort of basically told you. And in these observations, there are other remarkable exceptional events. We saw our second binary neutron star coalescence. We also saw a neutron star black hole coalescence. We saw a binary black hole, which is called an intermediate mass black hole. We saw a binary system which was asymmetric, so that subdominant modes could be sort of seen. So many things which you thought was not possible because of some astrophysical modeling, you are sort of seeing. So essentially, one has to sort of keep in mind that anytime we look at a universe by a more sensitive observation, you can say something more about the observable universe. So whenever you get data, what we do is a bunch of things. We send out open alerts so that our astronomy colleagues can look for counterparts. We identify what we call as exceptionable events. When the full analysis is done, we create a catalog, and in the catalog give the parameter for each of our sources. From that, we infer the rates of these coalescences, properties of the population, and once you know the properties of the population, you have to answer the question, how are they formed? So you have to say something about the formation channels. You can test the general theory of relativity, do cosmology, and we also started looking for, are some particular sources not independent sources, but gravitationally lensed kind of sources. So this kind of work is already also sort of being done. And in addition to coalescing compact binaries, there can be other sources, gravitational waves from isolated neutron stars, from supernova, and we try to look for whether such data, indications are there in our data. All this research is done under the umbrella of what is called as the LIGO India Scientific Collaboration, whose PI currently is Archana Pai of IIT Bombay. I am its co-PI. And it consists of 14 institutions in India, and currently it has about 112 members. And as I told you, on different aspects, different colleagues at different institutions do research coming from the LIGO data. The important point, after O3, we can make a guess by using our analysis and using population models that the binary black hole rate per gigaparsec cube per year is in this particular range. The binary neutron star is in this particular range, and the neutron star black hole is in this particular range. As the population increases, these intervals will become more and more sharper. So as I sort of told you, I have focused on coalescing compact binaries, but we also look for gravitational waves from supernova, from gamma ray bursts, and so on, from isolated neutron stars. And we also look for gravitational waves which are a stochastic background. Sometimes you may not be able to identify single sources, but they may all add together to create a background. So there may be an astrophysical background, or there may be a cosmological background like the CMBR, and we look for them by different kind of techniques in our data. So that's where we are today. So in the last few minutes, where are we going? What happens every year is the LIGO Scientific Collaboration puts out what is called as its program for the coming year. So now the third observational run is over. So in 2022, we are preparing for the fourth observational run, and we have put together this particular document, which will basically tell you that this is what we are going to do, this is the kind of analysis we are going to do, and so on. So anybody who's interested can look at this document, which is a public kind of document. And then you will basically see that we are going to start the fourth observational run starting 24th May. This will be a much longer run, 18 months long, with 2 one-month breaks in between. So total will be about 20 months. And we will be more sensitive. So for example, what you should compare here is in the third observation run, we could see the LIGO could see up to 140 megaparsec. Because of our improved sensitivity, we hope to go up to 190 megaparsec. And similarly, the other detectors will also see further. And the Kagra detector will start functioning also in this particular epoch. So we have 3 detectors, and therefore we can ask the question, how many events do we hope to see? And if the Kagra sees that particular event, how much will be the improvement in the sky localization? So you can see here that because there was only 2 detectors, a few hundred square degrees was the sky localization. But on an average, because of the 3rd detector, you will do even sort of better. So your chances to do astronomy is definitely going to increase with O4. Does our story end there? Now we have become greedy because we know that there is a big, universe to be sort of discovered. So already there are plans to go beyond what we call advanced LIGO by something which is called A+. Beyond A+, 4 years from now, there is something called A sharp. And there is something later which involves, slightly new and undeveloped kind of technology, which is called the Voyager. There is a space detector which is already being sort of planned. This is called LISA, and this will happen in 2034. This has been sort of funded by Europe, the ESO, and the NASA is a participant in here. It's a detector in space, not a few kilometers long, but 2.5 million kilometers long. Why do you need such a long kilometer thing? I'll come to in a moment. Beyond the 2nd generation detectors, the 3rd generation detectors are being planned. This is a detector in Europe, which is called the Einstein telescope, which is a 10-kilometer long detector, which is a triangular configuration. It's supposed to be underground. And a project which is proposed in US, which is called the Cosmic Explorer, which is a 40-kilometer detector and a 20-kilometer detector. Our science drivers are always the following: gravity when it is extreme, matter when it's at very high densities, and putting them together, what is to reconstruct the cosmic history of the universe. With the 3rd generation detectors, you will be able to detect a significant fraction of all the mergers which happen in the visible universe. You can see that you can see till the end of the universe. And you may be able to detect the mergers even before the first stars formed. If there are primordial black holes, then they will be seen by these 3rd generation kind of detectors. I have to sort of end by telling you all that I have talked to you about is by detectors on the Earth, which are in the hertz to kilohertz range. We really have space detectors because we want to span gravitational waves in the millihertz range, which happens from supermassive kind of black holes. There is a search for gravitational waves by using pulsar timing arrays, and of course, gravitational waves from the Big Bang itself. So the important point is that the gravitational wave frequency also spans 2 decades in frequency, just like the 2 decades in frequency which we have in electromagnetic radiation. And as I basically told you, there is the possibility of doing multi-band. That means seeing the source here and then seeing it here, etc., and so on. And the observational things which I want to point out is that I hope that LIGO India happens, because that is one thing which is an observational facility which will tell us about gravitational wave astronomy in India. And for gravitational waves in the nanohertz band, there is something called the Indian Pulsar Timing Array. The UGMRT is part of this particular kind of process, and this will basically look for gravitational waves in this frequency band. So you can see here that there is a possibility to participate in these 2 bands, and of course, something else will happen in the next few decades, and there are more and more opportunities to come here. And therefore, essentially, we are in a situation where we begin with what Rumsfeld called known knowns and known unknowns, but ultimately, of course, our interest in what is the unknown unknown. And we have all these kind of detectors and all these kind of sources which we know should be there theoretically. Therefore, in 2021, the gravitational wave community put together a document which basically looked for where the subject will go in the 2020s and 2030s, and anybody who's interested in it can look at this Nature Review Physics article. So let me conclude. Black hole astronomy was ushered in by this particular source, and multi-messenger astronomy with this neutron star source. The game changer was the network of the LIGO and Virgo detectors and their ability to localize a gravitational wave source to a small enough region and send alerts to facilitate an electromagnetic follow-up. The future network, as I explained to you, first brings in Kagra and hopefully LIGO India in the future. The third observational run has consolidated new insights into astrophysics, cosmology, and fundamental physics, which were only assessed feasible earlier, and that remarkably emerged with the first discovery of gravitational waves from binary black holes and a binary neutron star. Our analysis is just completing, and as I explained to you, we are preparing for the next observational run. So, to conclude, the first faint strains of the gravity wave symphonies are the whispers of a new astronomy. It is opening a new window, and once you have a new window, new interfaces emerge between general theory of relativity, quantum field theory methods, and high energy physics. So with that, I would invite you to decipher the universe by using gravitational wave observations and multi-messenger astronomy. This is what we have achieved till now. What is remaining to be discovered is even more. Thank you for your attention.
Thank you, Bala. Very excellent overview, journey from 1916 to now and the future direction. Thanks.
Thank you.
Now, question?
So what I want to understand is what is the cause of the delay between the gravitational wave observation and the for electromagnetic observation? So
What is the
delay, why? What is the cause of the delay?
Yeah, so for that you have, so that's where it gives you a job for the theoretician, right? So the basic point is, one thing it can say is it saying something about the detailed physics of this particular explosion? Or is he saying something more fundamental about the speed of gravity versus the speed of electromagnet? So these are the kind of questions which are sort of explored. You try to sort of model and try to ask if a particular theory is correct, what kind of prediction it will have about the delay times and so on. So it says something about the model for the gravitational wave emission and the electromagnetic emission.
So, from the multi-messenger astronomy, before the discovery of gravitational wave, we were completely dependent on model for the fitting. So, after multi-messenger astronomy, did we find some corrections in the Einstein's theory of general relativity?
Not yet. So, as you rightly say, that is the exercise which we really want to sort of do, and we keep doing. So, at this particular point, we keep sort of saying, what is the, to what extent is the data consistent with the model which you use, which is the general theory of relativity and the related astrophysics, etc. And you put a bound on what is the extent to which the observations are consistent with the particular theory. Once you find a violation of that in one of the observations, you will say something about the kind of corrections which Einstein's general theory of relativity will need to be done.
Thank you, sir.
Okay. If no more question, thanks, Bala. But so, okay, on the behalf of the school, I'm giving the painting of the TIFR.
Oh,
so all the
thank you very much. So I painted for you the universe with gravitational waves. Now I have a real painting in
of TIFR. This is the local artist, local tribal people.
Okay. Very good. Thank you very much. Okay. Thank you for your attention, and I hope that many of you will join this particular case. I am on my way out, but we need 10 times more people to explore the gravitational wave universe. So welcome to the gravitational wave astronomy.
Okay, now This is the backing.
Yeah. Okay.